Hello, everyone. We're going to start a new unit, starting with Chapter 6 on thermal chemistry. And thermal chemistry basically says that we're going to look at heat or energy as it goes into a system, into a chemical reaction, or out of a chemical reaction. Okay, so it's energy in or out. And as you know, as we discussed further, anytime a chemical reaction happens, it is this flux of in and out of energy which determines whether the reaction feels hot or feels cold. Okay, so when we talk about energy, there's several energies. We're going to look at kinetic energy, which is the energy of movement or motion. That was in Chapter 5 on gas laws. Potential energy is, of course, stored energy. Won't talk about that too much, but again, anything that has bonds can have stored energy. Anything that makes bonds, actually the process between the two, can release or store potential energy. And then we have electrostatic potential energy, in other words, called the Coulomb's law, and that's the charges over the radius. It should be squared, but that's not a big deal for now. And then energy is, of course, measured in joules. So you'll see a lot of joules or kilojoules, okay, which is 1,000 of those joules. And then we'll talk about this idea between work and heat, okay, with internal energy of a system, okay? So when we talk about a substance that is going through, or at least a situation in which there is a chemical reaction or a process happening, could be a physical reaction or physical action, we have to define the system. The system is the portion that we're going to study. The surroundings is literally everything else. Okay, so you have to define what the system is. It could be a beaker, it could be a test tube, it could be our classroom, it could be Stowe, it could be the world. Okay, well, it could be the entire universe. But you need to actually define that. Okay, now versus the system and the surroundings, what we have here is we have the following reaction. So we have water, hydrogen gas and oxygen gas creating water. So when we look at this, you'll notice that this is the system. This is what we're looking at down here, okay? This is our system. Everything else is the surroundings, okay? So the system includes the reactants and products, and of course you can see those. And again, the surroundings is everything else. So now energy loss and energy gain, of course, we know these to be exothermic and endothermic reactions, okay? Every reaction, whether it's chemical or physical, it has to have an input energy in and energy out. Now, the net of these things, if you have more energy out, it's going to feel hot. Okay, energy goes in, but tons of energy comes out. We call that an exothermic reaction. In other words, energy is lost from the system to the surroundings. Okay, anytime you have to pump energy in really hard, a bunch of energy in, and very little comes out, we call that an endothermic reaction. In other words, the net gain of energy from the system to the surroundings, okay? So there's more energy in, so this one will feel cold, than energy out. Okay, this reaction, endothermic reactions tend to feel cool or cold. This is what it looks like for an exothermic reaction. And again, you'll notice you start off with reactants really high. These are reactants, these are your products. I call this a downhill process. And when we look at this, we notice that there is a net energy loss of this. This is the energy that goes here, okay? So you'll see an energy loss in the form of heat, okay? So this one feels hot. A couple things on this. Notice this is the energy here, and this is the reaction pathway. You go from high to low, okay? Loss of energy is in this here. Now, every reaction requires what's called an activation energy. It's the energy that you have to use to get over the hump. And that energy is right here, okay? You have to add in a little bit of energy. Notice it goes up, energy goes up to this point right here, and then the full amount of energy is lost here. So you have energy in versus energy out gives you this net here. This is the net. And notice most of the energy is out here, and you end up with heat, and then you end up with something that feels a little bit warm, okay? Let's look at an endothermic reaction. An endothermic reaction is the opposite now, okay? So now heat has to go in, or energy has to go in. Notice you have to pump in all this energy to go up here. So that's energy in. And then some of that energy comes out here, okay? So notice most of this stuff is energy in, very little is energy out. So I always said it involves these two processes. You have to pump energy in and energy comes out. The net of those gives you an endothermic or exothermic reaction. This one's endothermic because I put in way more energy in than I put out. Okay? So notice reactants are on the bottom and products are on top now. So I had to add in energy to get to there. Okay? The exchange between system and surroundings, this is just a graphic on this. We'll go into this a little bit more. But I want to show you something, okay? Q is first heat. Heat is Q. Notice, guys, anytime energy goes in, it's positive. Anytime energy comes out, it's negative. This is endothermic. This is exothermic. Okay? So we have to deal with that too. Okay? Negative Q, positive Q, what that means, it's not necessarily on the number line. The negative and positive actually gives us a value of what direction the energy is going. More on that later. The internal energy as a system is basically summed this way. Again, that's a balance between what's going in and what's coming out. And actually, let's talk about that just a little bit further. So as far as internal energy goes, again, this plays off the fact that it's all about a balance of in and out, okay? So again, depending on whether you have more in or out, you see this particular system. But so here's another graphic on what you see here. So energy absorbed versus energy released. Again, that further explains what I've been talking about, okay? We'll look at this slide in class. So I mentioned this already. The negative and positive actually stands for direction. Okay, you don't have to put a positive there. That's why I didn't type it in. But not only do you have a number, a value, a quantity, but you also have a direction. Exothermic means energy is leaving, so it's negative. You're taking energy out of the system, or energy is coming out of the system. Endothermic means energy is being added. Okay, positive and negative shows direction. We need those negatives and positives. So heat and work basically is Q plus W. Okay, the internal energy of a system says that we're going to add Q and W. So this is one aspect of a system here. And actually, when I talk about a chemical reaction or something doing work, it basically involves gases expanding or contracting, and it gets a little dicey on how to interpret this. So again, Q plus W, I'm not going to spend a whole lot of time on this, but and again, we're going to talk about state functions versus path functions. Again, right now, I'm just going to move forward here. We're going to now calculate delta E. So delta E, which is the internal energy of a system, says we're going to take the amount of heat, whether it's exothermic or endothermic, and we're going to add that to the amount of work, whether it's exothermic or endothermic. And you have to read the question to determine that. So it says the system is going in endothermic process in which 15 kilojoules of heat flows. So that's 15 kilojoules of endothermic heat. Endothermic quantity, and that's kilojoules, plus it says 1.4 work is done on the system. So that means work is going into the system. That's plus 1.4 kilojoules. And we end up with a value of 17.0 kilojoules of energy. That is the internal energy of the system. So energy went in and work went on it. Okay, both going in, both endothermic. Okay, so this actually describes that a little bit more. When the energy is exchanged between the system and the surroundings, it is exchanged as heat or work or both. Okay, so in other words, most of the stuff we will do in chemistry involves just Q, just Q. If it involves gases, now gases can expand or contract, also causing work to happen. That's basically steam engines, okay? So, yeah, so that's delta equals Q plus W again. But again, heat or work or both. For most of the things we will do, it will involve just Q, and more on that later. Okay, so now work. Again, we don't deal with this too much, but I just want you to know. Okay, so here I have a solid plus aqueous, and I produce a gas. So if I didn't have any gases over here, but here I have a gas as a product. That means gases were produced, and the system is going to do work out. Okay, so if work is being done by a gas, and this is what we have here, this whole system is expanding. So in other words, if I were to take this reaction, and actually this does happen, if I take zinc metal and throw some acid in it in a balloon, I get this stuff, and the balloon starts to inflate because it's producing a gas where there wasn't any gas before. So it's expanding. So what is that? That means work is being done out. So it's negative work. Okay? And notice positive volume. So let's take a look here. Let me just erase this because there's a lot of stuff up here. If I take a look at this, how do I know what work is being done? I apply this equation here. Okay? So yes, delta E is equal to Q plus W. So how do I get work? Again, it has to do with expansion or compression or contraction of gases. That's all it is. Okay? Expansion or contraction of gases. So if I'm producing a gas, it's going to expand. Produce a gas, expand. Okay, that means work is being done out. It's negative. and it's expanding, so I have a positive delta V. Delta means change in. So the volume goes up, it gets bigger, it grows, it expands. Okay? Now, if I take the reverse of this reaction, and I take hydrogen gas and react it with zinc, I'm using up these moles of gas. Now I'm creating 0 moles of gas. And since I'm using up the gas, I now have work being done on a gas. In other words, since the work is being done on the system, it's positive. And now it's shrinking, it's getting smaller, it's being compressed, it's contracting. And I have negative volume, okay? Negative delta V. And again, that plays off of this, and this plays off of this equation here. So, to summarize, how do you know this? What's an easy way to remember all this stuff? You basically identify this. The signs of work and delta V have to be opposite. And the reason is that negative sign there. Okay? And it makes sense too. If work is going exiting the system, it means it's expanding the system, it's expanding the surroundings, or it's expanding itself, I'm sorry. And then you end up with a positive volume. It gets bigger. Okay? The volume increases. If work is being done on a system, then you're going to compress the system, and you'll end up with a negative volume, a negative delta V, not negative volume, but negative delta V. This graphic is nice as far as showing us the interrelationship of these things. So you can check this out at your leisure. Okay? Let me move that out of the way. So I'll give you a chance to write that down. You can pause it at any moment, of course. Okay, we'll do some of these problems in class. Again, I'm not going to get into them just yet. Again, this is a whole bunch of stuff. So that's good for now. But that's internal energy, okay? Again, to summarize, it involves pressure, it involves work and Q, which is heat. Most of the stuff we'll do does not involve work. It involves Q. And there's tons more on Q in the next video. Okay? Again, if you have questions, email.